Hello, my name is Doga Tekin, and I'm a member of technical staff at Oracle Labs Zurich. Welcome, and thank you for joining to this session on object trajectory prediction using AutoML on Oracle Autonomous Database. We will start with an introduction on what object trajectory prediction is, and more specifically, what vessel trajectory prediction is. We'll talk about how we accessed the vessel traffic data we used in this project. We'll talk about some related work that we researched before starting our approach. Then we'll dive into the approach. We'll talk about how we processed the data, how we modeled this problem as a machine learning problem, and how we used auto machine learning or AutoML to solve it. I'll then walk you through some experimental results we obtained and show you a visual demonstration in Spatial Studio. I'll conclude with some summarizing remarks. So what is object trajectory prediction? This is the problem of predicting where a moving object will be at some point in the future. This is a very general definition, but it can apply to many different things. For example, it could be about predicting where a plane will move to in a certain amount of hours. It could be about a ship. It could be about a car. It could be about any moving object or entity. In this project, we're specifically focusing on ships or vessels in a more technical language. So we will present an approach for predicting vessel trajectories using publicly available data and the auto machine learning capabilities of Oracle Autonomous Database. We will also visualize the results using Spatial Studio, which also is included with Oracle Autonomous Database. So at a very high level overview, this is how this looks. We start with some vessel traffic data. This is ingested to our Oracle Autonomous Database. This lets us run first AutoML on this data, which basically takes this data set and chooses the best algorithms to run on this data set, chooses the correct sample of the data, the best features among the data, and it tunes a model for us to make predictions in an efficient way. And the second thing the database enables us to do is to visualize all of this interactively in real time in a very nice map visualization in Spatial Studio. So how do we obtain this data? This data comes from the US Coast Guard. It's called the AIS data, or Automatic Identification System data. It's collected by the Coast Guard through an onboard navigation safety device that transmits and monitors the location and characteristics of vessels in both US and international waters in real time. You can use the link at the bottom right to learn more about the data and also access it yourself. This is just a very small sample of how the data looks. So each ship has a unique identifier called an MMSI. And each data point in this data gives us a specific timestamp down to the second, a latitude and longitude of where that ship is at that specific timestamp, the name of the ship, the type of the ship in terms of these numbers that can be mapped to different ship types like cruise ship, tanker ship, and other types, and some other columns that we aren't using right now in this project. We started with some literature review of relevant papers. These included AIS-based vessel trajectory prediction, deep learning methods for vessel trajectory prediction based on recurrent neural networks, trajectory prediction for vessels using historical AIS heat maps and long short-term memory networks. And we've even looked at aircraft position prediction because, as I said, object trajectory prediction can apply to many different objects, and some of the knowledge or approaches can be transferred between these domains quite easily. And in the end, we've come to the realization that if we model the problem well, and if we process the data well, and if we use the capabilities of AutoML, even a simpler, more intuitive approach can work well on this problem. And that's what we're going to present today. So how do we process this data that we obtained from AIS? As I showed, it has information down to the second in these timestamps, but in this project, we were actually interested in a higher granularity, just hourly predictions. Where is the ship going to be in the next hour, in the hour after that, in the hour after that? And a vessel might have many small movements in a single hour, but as I said, we are more interested in this project in the overall long-term trajectory of where that ship is moving. So we create a data set to fit this use case by calculating the average position of each vessel in each hour to obtain a simplified table. This is how that looks in practice. So let's assume this is the raw data. So we have the latitude and longitude of a ship at hour 1, 15 minutes in, and another position at hour 1, 45 minutes in, and then some positions from the second hour at different times into the hour. What we do is we average those locations in each hour to obtain a simpler table where we know that this ship at this hour was on average at this location. And in the second hour, on average, it was at this location. And this is how we process the whole data to start the problem. Now that we have the data, how can we model this problem? We know the historical location of many ships. We can train a model to predict either the next specific absolute location of the ship or its next change in location. So what I mean here is, let's say for the first 3 hours, we know the latitude and longitude of a ship, and we want to predict where it will be on the 4th hour. One option is for the model to directly output a specific latitude and a specific longitude value. This is predicting the exact next location of the ship. The other approach is predicting just the change from the last hour, kind of the delta movement from the last hour. And of course, you can use this change in location with the previous location to find the absolute next location as well. So they lead to the same result, but they're just different approaches that we considered. And we thought there were some negatives about trying to predict the next absolute location. One was it has a higher potential for bigger mistakes. So if you're predicting the next absolute location, latitude can range from -90 to 90 degrees, and the longitude can range from -180 to +180 degrees. And longitudes also wrap around. So 180 degrees and -180 degrees are actually corresponding to the same point on our world. So this can confuse a model naturally, and it can make bigger mistakes due to the range. But instead, if you focus on predicting the next change in location, first, there's a lower potential for big mistakes. Most ships can't move so much in an hour. So these changes will mostly be in the range from maybe -0.3 degrees to 0.3 degrees, which is, in terms of latitude, maybe 30 kilometers at most in an hour. And the next advantage is these changes are generally nicely distributed around 0. And there's no wraparound problem for this change where a minus value and a plus value are actually the same. So that's what we wanted to focus on. And the next thing to decide in problem modeling is what features might be interesting for this problem. So we know that we want to predict one model to predict the next lateral movement, so the next change in latitude, and we want to predict one model for the next longitudinal movement. What should these models look at to make these predictions? Well, one thing that makes sense is to look at previous movements. How has the ship been moving recently, so that we can predict how it will move in the future? Secondly, where is the ship currently at, the current absolute position of the ship? A ship might move differently when it's closer to a shore versus when it's at open sea, or when it's on a specific route that most ships follow. So this is important information. Then the vessel type is, of course, important. So a tanker doesn't move the same as a cruise ship. And finally, time could be important. For example, ships might move in different ways in different seasons, or different weeks, different months, or even different times of day. And one important point here is both the latitude predictor and the longitude predictor, when it's looking at the previous movements, it's looking at the previous movements in both directions. So the latitude predictor is not just looking at the latitude movement, it's also looking at the longitude movement, because both of these are kind of dependent and affect each other. So these models that we presented in the last slide, they can be used to make a prediction 1 hour into the future. And specifically how we designed it is, it uses the previous 5 hours movements to predict 1 hour into the future. But what if you're interested in predictions further into the future? What if we want to know where the ship will be in 4 hours? The solution here is we can feed the model's predictions back into it as inputs to predict further and further into the future, almost arbitrarily. So as an example, let's take the example I said, we have the last 5 hours information and we want to predict up to 4 hours in advance. The first thing we do is we take the last 5 movements and we predict the next hour's location. Then we kind of scrap the oldest data point and we take our new prediction as kind of the current position of the ship and use the previous hours as the previous 5 hours. And then we can make a new prediction for 2 hours into the future. And then we can treat that as the input and get a prediction for 3 hours into the future. And we can keep doing this as far as we need to. So now we have the problem defined, we have the data processed, and we have the potential features decided. We need to select and train a model that can perform well on this data set, and we need to select the best features, and we need to tune the parameters. AutoML makes this easy for us. So AutoML takes the data, it identifies the top algorithms that could perform well on it, it adaptively samples a subset of the data to evaluate the approaches quickly, it selects the most relevant features for the problem, and it tunes the best algorithm for the problem for us. I won't go into the details of how AutoML works, but there are different sessions at CloudWorld this year where you can learn a lot more about AutoML and explainability and how it works. And you can also see applications from different domains about oysters, about healthcare, about anomaly detection. So AutoML is integrated with Oracle machine learning inside Oracle Autonomous Database. So the advantage is it can directly use the data we have in our Autonomous Database as long as we've ingested it there. So this is kind of the introduction UI where you can go create and run AutoML experiments. You can manage your models you've trained. You can go into notebooks and explore them further. And if you go to this AutoML UI, the first button, we will be able to run experiments. This is how an experiment often looks. So the workflow here is you don't need to write any code. You just load your data. You set a time budget, the time you have to run these experiments. You pick the task you want to solve and the target column that you're trying to predict. So in this case, we're solving a regression problem. It's a continuous variable. And the target column in this experiment is the next change in longitude, this delta longitude that we call it. We select the metric to optimize. Let's say we're optimizing mean squared error in this instance. We choose the candidate models to try. Let's say we want to see if a support vector machine or if a neural network will perform better on this problem. And we just let AutoML do the rest. It will analyze the data, it will run the models, it will sample the data and features, and it will return to us the metrics that we wanted to optimize. So we can choose which model seems to perform the best. And even more, after training the models, it will also analyze the feature importances of the data set for us. So if you look at this example of trying to predict the next longitudinal movement, we can notice several things. First, the more recent movements of the ship seem to be more important for predicting the next movement. This makes sense. The latest movement of the ship in the last hour is probably more important in predicting than the movement 5 hours earlier. And we also noticed that the previous longitudinal movements of the ship are more important in predicting the next longitudinal movement compared to the previous lateral movements. This is also quite intuitive. But note that they are not at zero importance. So the lateral movements still play some part in the predictions. So now we've trained the model. We've seen which features were important for the model. If we still want to dive deeper into them, AutoML lets us do that by generating these Oracle machine learning notebooks automatically. Just from the UI, clicking Create Notebook, we see this view where the data is loaded for us automatically, the training data is prepared for us, the model we pick is trained for us, and the details are shown. And we can use this to access the data and visualize it. We can see the details of the model, use it for inference on new data points, and we can draw plots for evaluating our model. So here are the results for predicting 1 hour into the future. In particular, we're focusing this demo on 7 tankers that had a lot of movement, so interesting data to explore. And we did the training on data from 2020, and we did the testing on data from 2021 and 2022. These two plots are helpful in understanding the performance of our models. The left one is for the latitude changes, and the right one is for the longitude changes. You can see on the y-axis the true values, and the x-axis shows the predicted values. And each data point here is one example in the test set, showing both its true value and the predicted value. So a perfect model, perfect guesses all the time, would fall on this red line where the true value and predicted value are always the same. Yeah, and you can see that even though our models aren't perfect, they're packed quite tightly around this red line. So there aren't any big mistakes, whether the true value is at 0, the ship is stopped, or whether the ship is moving very fast, around 0.2, minus 0.2. We can see that the predicted value for each data point is always somewhat close to the true value in both latitude and longitude cases. So this is of course promising. But we're also interested in 4 hours into the future. And we can do this, of course, first visually by plotting the actual paths of some ships with the predicted paths. But we can also compute some average error percentages or absolute errors. And we noticed that 1 hour into the future, our model is less than a mile off on where the ship will be. And 2 hours into the future, this error goes up to 2 miles. And 3-4 hours into the future, this error continues going up, of course, because the ship keeps moving, and we're basing the next predictions on previous predictions. So the error is propagated and expanded, but it still doesn't deteriorate that badly. Even 4 hours into the future, we can guess where the ship will be with about average 6 miles off accuracy. So here's a small GIF animation of how the ship is moving and how the model is predicting. The blue points here are the previous 5 movements of the ship that are used for the prediction, and the red points are the 4 next predictions of the model. You can see as more data comes in, as the ship keeps moving, the predictions always adapt and update themselves to predict most accurately the next 4 hours. And here's another way to visualize all the results using Spatial Studio. That also comes in Oracle Autonomous Database. So here we're looking at the world map, particularly the seas, and we're visualizing in red the actual paths of the ships in the data, and we're visualizing in blue the predicted paths of the ships. And we can also overlay other information like port locations, and any other data you would like to stream into Spatial Studio. So if you focus and zoom in on one of these examples, you can see that these blue predictions are predicting the ship will slant left in a while. And you can see from the red path, after a while, it does indeed start turning left. And of course, the predictions for some ships in some locations are better. For some ships, for some locations, they're worse. But overall, we can see a good overlap between predictions and true paths in this example. So to conclude, I'll just summarize what we've talked about in this presentation. We processed publicly available vessel traffic data to obtain a data set of hourly positions of ships. We modeled the problem as a prediction of the change in position in the next hour based on the previous movement's current position and time. And we've also used this to predict arbitrarily into the future using old predictions as inputs. We used auto machine learning on our data in Autonomous Database to quickly obtain high performance and explainable models. And finally, we visualized these true and predictive trajectories using Spatial Studio with our data. Before I wrap up, I would like to acknowledge that this work was done in collaboration with and wouldn't be possible without significant contributions from Tim, from NSG Cloud, he's an NSG Chief Cloud Architect, and Daniel, who's a consulting member of technical staff from Spatial and Graph. So thank you both. And With that, we're wrapping up the presentation. I've put my email there, so feel free to reach out to me if you have any questions about this work. And thank you for listening.